Hi guys, I want to give you a little background, a little run through of what your lab is going to be for tonight. This is week 7, and if we were in class, we would be doing some really cool hands-on investigations looking at starlight and spectra. And of course, I love Pink Floyd. And if you are familiar with this album cover, even if you're not, you can see that we have white light that's entering on the left. The triangle represents a prism that is then breaking apart the light into its component colors as it leaves the prism on the right. So just as a little recap of visible light, we know that all light and all color has a specific wavelength and frequency, and that is what defines whether something is violet or red. And here we can see what those numerical values are of each of those colors. And we're going to look at that in a bit more in a second, but we can see that there's a numerical value of violet, which is different than the numerical value of red. And that has to do with the physical size of the wave, which is called the wavelength. And that has huge implications for how we study astronomy, where we study astronomy, and the resultant spectra that occurs from things. So just to revisit that order, that's how you see the order of the colors all the time: red, orange, yellow, green, blue, purple, or violet. If you've memorized Roy G. Biv, that's because that is always the order because of the size of the wave. So some terms here: wavelength is the physical size of the wave, and that goes either from trough to trough or peak to peak, not peak to trough. That would be half of a wave. This is one total wave, which would be the same size as if you did it the other way and went peak to peak. That would be the same size. And amplitude has to do with how tall the wave actually is from the middle. So here we can see the physical size of each of those colors, and this would be a model of each of those. So you can see that red is physically a longer wave, so it's a bigger wave, which means you have less of them over the same period. And that also has less energy, whereas your violet has more energy because the waves are smaller, so you have more fit into a tighter space. That has to do with its frequency. So here, if we count them, we have 1, 2, 3, 4. But if we count them here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So violet occurs 10 times, and our red only occurs 4. So we can count that as the frequency, the number of times it occurs. Because violet occurs more times, it has a higher frequency, but a smaller wavelength. They are inverse. If you think about the wavelength of infrared, IR, would be right here, and UV from the sun is right here. So we could just extend this model to where infrared has less energy and a longer wavelength than red, and UV has more energy and a shorter wavelength, higher frequency, than violet. We can just extend those out. That's why UV is dangerous, because it has a higher energy. But it takes all of the wavelengths in order to make these beautiful astronomical pictures. So all of those waves in visible light, that's only such a tiny portion of the electromagnetic spectrum. And here we can see a beautiful image of the Andromeda galaxy, but this is not invisible light. This is actually an overlay, a composite of multiple types of light. This is most likely radio, which is overlain with infrared. Infrared is actually the most commonly used wavelength in all of astronomy because we can see the infrared universe provides a lot more information than the visible universe does. So here we can see each of those components of the electromagnetic spectrum. Radio waves with our extremely long waves here, and gamma rays with our really short waves here. And remember that the energy is directly proportional to the frequency, which means the number of times it occurs, but inversely proportional to the wavelength. Longer wavelength, it occurs less times. there's less waves. Shorter wavelength that occurs more times. That's why gamma rays are more dangerous than radio waves. And we see these in our everyday life, except for gamma rays. Those really don't penetrate Earth's surface because of our atmosphere, but radio waves do. And these have implications for how we do astronomy because we see all of these in space. And this is an inaccurate model because it shows them as all even, but really radio waves make up over half and visible is a teeny tiny portion. So because we have an atmosphere, not all of those wavelengths penetrate to Earth's surface. So these are our atmospheric windows. So if we were to take a look at that, we can see that the visible window is right here. That's why we see in color. So that's visible light. It penetrates all the way to the ground. Here you can see there's a window too. That is where radio waves are. So we can detect visible light and radio waves from Earth's surface. But here we can see some other little dips. That is for part of the infrared spectrum. If you remember back at the beginning of the semester, I showed you a picture of a plane that I flew on that was a NASA mission. That's NASA's SOFIA mission that flies right about here. It flies in that atmospheric window and it detects infrared. It's not taking optical or visible pictures. So atmospheric windows are these areas where the atmosphere is transparent to certain wavelengths. So totally blocks out waves of this size, totally blocks out waves of this size, but allows these through. So we can do visible and radio astronomy at Earth's surface. We can't do the rest of them. And infrared is really important. It would be really cool if we could see an infrared, but we can't. If you think about heat vision, night vision, that's what the infrared is. So there are infrared cameras, and there's even an app you can get on your phone, which is supposed to use some sort of algorithm to be able to see that. So this is a bag. This was actually in my class, and we had something behind the bag, and these are the indications of different temperatures from that, and you can actually see those temperatures here. So the infrared universe, or the infrared astronomy, allows us to see things like collisions, star-forming regions, areas of gas and dust that could be potential star-forming regions, planetary formation. It provides so much information about the universe, more than any other wavelength, and we can conduct it by having a plane that flies every single night. It's more reliable and easier to fix than any other space mission. So we can see a collision between exoplanets. But tonight, we're not just looking at different types of electromagnetic waves. We're also then expanding that to look at spectra. So every gas has its own unique spectra, just like every color has its own unique wavelength. If we were in class, we'd be looking at gas tubes just like this, to be able to see what their spectra looked like. So you would be looking at all of these gases because these are gases that are common in the universe. And by looking at these, we can make connections and inferences about the compositions of stars. Also things like the velocity and the motion of stars. And if we can tell the composition of stars, we can tell what phase they are in their life cycle. We can see what heavy elements are there. We can tell if they were formed as the result of a collision or of a supernova. So that compositional information is really crucial for our understanding. For example, we can look at the sun and see that the sun has elements of salt, of sodium, and gold. How did that happen? So it allows us to do a lot of investigation by analyzing that spectra and that light. So if we were in class and we were to look at that spectra, this would be what it would look like. We would be holding something up to our eyes called a spectroscope. And what it does is it shows us these lines. These are called spectral lines. And this is an image of what you would probably see looking through that. The numbers are the numerical value. So you can see the red is always closer to the bigger number, bigger wavelength. So these two are opposite because sometimes depending on how you hold it, you can see it on either side, but the blue would always be the shorter and the red would always be the longer. So we can tell by looking at this then what the composition necessarily would be. So here you can see nitrogen has a lot of red spectral lines and lithium has a really prominent green line here. So for stars like our sun, we would expect to see a lot of hydrogen and helium. So, and then you can see the oxygen has a ton of blue lines. So these are the fingerprints, just like you have a fingerprint. These are the fingerprints of the elements. They always appear this way. So astronomers would use this to try and look at what the compositions of certain stars were, or even regions of the universe. Even planetary surfaces and atmospheres, we can use spectra to be able to gain that information. So looking at the sun, we can see some different types of spectra here, and this really leads into what our lab focus is. So we can see the outer layers of the sun. In here we see one type of spectra. There are three. This is a continuous spectra where we see every color. But then because the outer layers of the sun are so much cooler than the inner layers, those outer layers absorb certain wavelengths. And we see something that looks like this, called an absorption spectra. And the location of these lines are directly correlated with the elements that this gas passed through. So by looking at an absorption spectra, we can tell the nature of the material that these photons of light passed through. So it tells us about the solar atmosphere and the solar surface because it's absorbing those bands of light. All right, taking a look at your lab for tonight. Taking a look at your lab. Looking at week 7 for starlight, here is your lab. I'm going to walk you through that in a second, but I want to make sure you see that I've posted 3 videos. Please make sure you watch these videos. This one's really interesting about different colors of stars. Please watch it. They're all quick. This guy has the best accent of any narrator ever using the spectroscopy of stars. I suggest you start here, and when you get to part 2, watch this video and this video. So this one specifically talks about the 3 types of spectra. So here you're going to start, watch spectroscopy of stars and different types of spectra when you get to part 2. So here's your lab. Let's take a look. Please don't be intimidated by how long this is. There is a lot of reading material. After spending about 15 hours scouring the internet, I determined that there was not a sufficient simulation anywhere in existence on spectra. I spent a significant amount of time looking. I really did try. There is one simulation here that you're going to do to take a look at the properties of light. So that's where you're going to start. That is a PhET simulation. It is right here. It is pretty self-explanatory, has to do with the properties of light and bending light. If we were in the lab, we would be doing something just like this, where you were looking at bending light. So you're going to go through here using the simulation, answering the questions, follow the instructions. So here, one of the things to take note of with this is in the simulation, let me show you something because this is not entirely intuitive. When you get to the simulation that is taking its sweet time to load, here we go. This guy is what makes the light ray. So just to make sure you see that, you have to actually click on the red thing on the laser. That took me a second. So just make sure that you see that because it doesn't necessarily tell you to do that. You're gonna look at it and go, what the heck do I do? So that's what you do. So just make sure you see that. Okay, so here we're looking at refraction and bending light because the atmosphere does this too. So there are implications for astronomy based on the behavior of light and the interaction with our atmosphere. So here we have a section on prisms, again, clicking on that red dot on your laser beam. So here we get to part 2, and here's where I suggest you watch those second videos in Canvas. So here's where the reading really starts. And I apologize, I would usually not give you this much, but there is some really good information here. So it talks about gas tubes, the different types of spectra. in detail, and the videos will help you with that as well. You have a couple review questions here that have to do with atomic structure and what's happening inside an atom that makes you see a spectra at all. Here is part 2B in looking at atomic spectra and composition of stars. Make sure you see there is a simulation here. This is a short one. It didn't show everything I wanted it to. This may prompt you to make a free account. In that case, you just need to do it. So it will take you to this site right here. This is a decent simulation. So here you can see light coming from the sun being refracted through a prism, shows you the wavelength, shows you an intensity versus wavelength graph. Here you can see an atomic model. All of these are where it says n equals 1, that's the first orbital of an electron. You can see that this electron, it's denoted by a negative, is at orbital number 2. So if I notice now my electron moved. You will understand this once you've gotten through the reading, because the spectra we see is directly related to what's happening in terms of the electron. And make sure you see, like right there, it moved and it shows there was a blue little energy right there. So make sure you see that when you're going through this. You may have to click play a couple times. Here we can turn the telescope on. This is a little model of Hubble right here. If there's things you're unsure on, you can actually click on these and it will explain that to you. If you're interested in a little bit more, there is, where is it? Go back. Sorry, if you go forward, there's actually a little bit more there. So here you're just kind of experimenting with that. You may have to do it a couple of times, explaining what happens. Here is a little brevity of that graph. So here I have some questions for you. Make sure you're reading them carefully, describing what happens to the intensity graph in terms of the prism, the telescope, describing what happens to it when you look at both hydrogen and helium. So here showing that atomic model again, making sure you're circling in here what scenario would likely produce a blue photon. So there's nothing in here for this week that you have to screen capture. And then part 3, your reading and conclusions. So read through this information. This kind of recaps all of that on the nature of light, on spectra, on the EM spectra, and some representations of spectra. And here we're really putting together the implications for astronomy, looking at a solar spectra, giving some astronomical examples of where you would use each of these things. So looking at the spectra of a supernova remnant and the implications for some astronomical concepts like motion, like binary stars, like expansion of the universe, and then you have your analysis, which is only 3 questions. But that last one, you will need to spend some time writing up something that is pretty well supported. That is your weekly lab, guys. If you have any questions during class, I will be right there to answer any questions you have. Remember, you can do this alone or you can do this in pairs.